All right, so hello everybody. Welcome to our whole training sessions. The purpose of this sessions is to introduce you to our computational resource, which is called HAL, or Hardware Accelerated Learning Cluster. My name is Volodymyr Kindratenko. I will be conducting this initial introductory training, and then over the semester we are going to have a series of other training sessions where we will introduce different machine learning tools and then methodologies and techniques and so on. So the objective of today's training session is to introduce you to the machine that Center for AI Innovation operates. This machine was purpose-built to support deep learning community on campus and continues to be a go-to machine for this purpose. And so we typically, in the beginning of every semester, provide a training session where we introduce everybody to the machine. We describe the hardware of the machine, we describe the environment on the machine, and we show how this machine is to be used. And so that's kind of the purpose of this workshop. Before I get started, these are some reference links. We are going to post video recording of this training as well as this set of slides on our website, ai.ncsa.illinois.edu. But these are sort of the reference links that you can use to get more information or get started with using the system. The most important one is this main repository, which is a wiki page on the NCSA wiki space that describes the system and has all the system-related documentation and all the user guides and recipes of how to use it best and all that. So this is the main link. One of the sublinks or subpages on in this space is this new user guide, which describes how to get started with the system, starting from the point of how to request an account on the system all the way to how to use it for different purposes. The main repository, the main page also has a link to the Open on Demand portal. This is a web-based interface which enables you to use the system without being a computer science major. Essentially, this portal, and I will talk about this in the tutorial, this portal enables users to connect to a web-based interface and simply use web-based interface to develop models, to access the system, to run training, and so on. And there is also a status page which shows what the system is up to now. So it shows how many users are on the system, what jobs are running, which GPUs or how many GPUs are used, and so on. But we will talk about some of this later on. So just keep in mind that this first wiki page is basically all you need to find all these other things. Okay, as I go through my presentation, please feel free to ask questions in real time. Just turn on your microphone and start speaking, and I will hear you and I will be able to answer those questions. Let's get started. So first of all, what about name, right? So we built this system in 2019, 2018, 2019. This is a machine which was funded by the NSF. It was funded by NSF's Major Research Instrumentation Program. And we built this system from IBM servers with NVIDIA GPUs, which were state-of-the-art at the time when this machine was built. And we named it HAL. And it was named as a way to recognize that the first artificial intelligence machine in this Space Odyssey book that was published a long time ago was actually developed on campus in Urbana. So we kind of bore with the name HAL. So our machine is essentially one rack and a half of equipment, consists of 16 nodes. These compute nodes have 4 GPUs each, so altogether 64 NVIDIA GPUs. There is an all-flash storage, which is a very important component that we sort of learned the hard way, the importance of having the right type of storage and the right type of connectivity. All this is interconnected with high-speed InfiniBand interconnect, which makes the system to be a very capable HPC system and particularly suitable for running machine learning jobs at scale. So a few details about the hardware. The workhorse of this is our 16 IBM AC922 nodes. They have 2 IBM Power9 CPUs. Each CPU is 20-core CPU. They also have 256 gigabytes of DDR4 memory. So together, these are pretty powerful servers. Each server also has 4 NVIDIA V100 GPUs, which, as I mentioned at the time when we built this system, was state-of-the-art GPU technology available out there. These GPUs have 16 gigabytes of HBM2 memory, which still remains to be a rather sufficient amount of memory for many models. Although we see more and more models that demand significantly more memory than that. As I mentioned, there is an IB interconnect, and there are 3 of these DDN flash arrays which provide over 300 terabytes of usable space, all NVMe-based space. And there is a head node. There is actually a couple of head nodes which are used for login. So when you interact with the system, you log in into the head node, and from there your work is distributed to one of these compute nodes. So a few words about the compute nodes themselves. As I mentioned, is this IBM Power9 AC922 servers. Each have two Power9 chips, each with some amount of memory connected to it at a very high speed. And then what made the system unique at the time when we were building it was this NVLink interconnect between the GPUs and also going all the way to the Power9 chips. So a pair of GPUs is connected directly to Power9 chip at a very high speed. This is significantly higher than InfiniBand can provide. So which means that actually there is a very high speed interconnect between the memory, the CPU, and the GPUs, and also through the InfiniBand interconnect, high speed connection to the storage as well. And so that's what makes the system very capable. Just a few words about the Power9 CPUs themselves. I think this is a unique feature of this particular generation of CPUs that they supported NVIDIA's NVLink 2. They also provided PCIe Gen 4, which is what's used to connect to InfiniBand cards. And the CPUs themselves, they have 20 cores, but each core is SMT4, meaning that each core can execute 4 independent software threads. So all in all, you will see that the CPUs support up to 160 software threads. And in fact, in our reporting tools, these servers appear as if they have 160 CPU cores. So they physically have only 40 CPU cores, but for any practical need, you can think about them as having 160 CPU cores because that's how many threads they can run. And the GPUs, again, as I mentioned at the time when we purchased the system or these components for the system, these were state-of-the-art GPUs. So each having 15 teraflops in single precision, peak performance, and single precision is what's important for machine learning applications. So this is what the main sort of computational power that is used for training machine learning models. The other nice feature is the HBM2 memory, which provided 900 gigabytes per second bandwidth between the GPU attached memory, so this is HBM2 memory, and the GPUs themselves, which made this very, very capable system for machine learning workloads. And so there are 64 of these GPUs per the entire system, and we demonstrated distributed deep learning applications, such as ResNet 50, for example, trained on ImageNet, scaling literally linearly across the entire system while training on ImageNet. So the system is well balanced for the specific task of running machine learning workloads at scale. Okay, on the software stack, we run Red Hat Enterprise Linux. We provide the very basic set of compilation tools such as GNU compilers, NVIDIA HPC SDK, or the latest version or the currently supported version of CUDA, which is currently supporting the system. And then all of the machine learning tools are provided through the OpenCE, Open Compute Environment. This is a collection of open source tools such as PyTorch and TensorFlow and the relevant libraries, which are compiled for this specific architecture, which are compiled to support CPUs and GPUs in this specific architecture. So they are sort of optimized, optimally compiled to support this particular architecture now. So if you need to use a particular version of PyTorch or TensorFlow, you will need to make a choice of a particular version of OpenCE, and we try to compile the latest available versions of OpenCE whenever they come around, whenever they become available. On the software side, there is always a choice of several versions of this. So there is OpenCE. There is also an older collection of tools called PowerAI. You can choose which version to use through the environment modules. This is supported by the HAL mode, module system for dynamically alternate environments. And so typically when you log in into the system, you choose which modules or which components to use, which versions of different tools to use by using the modular command. Module avail command will show which modules are available or which packages are available. You can list the ones which are currently loaded. You can unload and load modules, specific modules that you need. So this is a sort of very basic tool that provides a very good functionality for the purpose of choosing and loading the software environments which have the tools which you need, specifically tools of very specific versions that you may need. So our users absolutely have to use this sort of interface to build a custom environment that is needed for their specific purposes. So how do we get onto the node, onto the compute nodes? So first of all, once you request the account on the system, this account request process goes in two stages. In the first stage, you have to submit a web form where you specify what purpose you are asking access to the system, and also for what kind of usage you envision. So the form is asking simple things like how many GPUs you envision to use and what. Once you do this, and once you also get at the end of the submission of this form, you get another link which you have to follow to request the actual user account. And once that user account is approved on the system, then within minutes you can start to use the system after that is approved. Very first thing that you need to do once your account is approved, you need to SSH for the very first time into the system, and you can SSH by providing your username and then the login of the server, the head node. Currently, HAL login 2 is enabled, so you have to SSH into the system for the very first time. When you SSH into the system for the very first time, so when you remotely connect to the system for the very first time, your overall environment is set up on the system. And once your overall environment is set up, you can just use our web-based interface to continue to work with the system. You no longer need to SSH into it. But for the very first time, you absolutely must SSH into the system to get the environment set up. And so you can use SSH to connect to the system, and you can use also other tools such as SFTP to transfer data into the system. But there are other ways to transfer data as well. We also maintain a different server to enable data transfers. So when you log in into our machine, into the head node, so is a HAL or HAL login 2, these are the two head nodes. When you log in into one of these, you are basically on the login node, whose purpose is to simply enable you to jump into one of the compute nodes in a manner that guarantees that only you have access to a specific set of resources, depending on what you need. In order to accomplish this, we actually have to run a workload manager. And so we run a SWRUN workload manager, whose purpose is to allocate resources and ensure that those resources are isolated only for you for the duration of your request to access those resources. So there is a collection of tools which come with SWRUN, such as SRUN, SINFO, SBatch, and so on, that you can use to request resources. Typically, our users have kind of two modes of operation. Either you can request access to a computational node for interactive use, and I will show an example of how this can be done. And typically you request this when you are developing a model and you want to modify something in your source code and then run it and see what happens, and then maybe terminate the execution after a few stages and then modify something else and run it and so on. So for interactive use. However, once you get your model to the point where it's debugged and it's working and it's producing the results that you expect to produce, and when you want to run it for many hours, when you want to train your model for many hours, then you will submit a job, computational job that will be submitted from the head node, will go into the queue of other submissions, and when there is available resource for that job, your job will be scheduled to run, and it can sort of run offline. You don't need to be present there. You don't need to be logged into the system. Your job runs when it gets scheduled. It finishes when it finishes. You then can come back next day, for example, if you launched your job to run overnight, your training session to run overnight, you can come back next day and you will see the results. The results will be stored in a couple of output files. You should be stored in your username, in your home directory. So these are the two modes of operation: the batch, where you submit something and walk away, and interactive, where you actually continuously work with it. So there are some limitations. Of course, we have a lot of users, and typically during the semester we have more users than we can sort of accommodate in a given moment of time. Therefore, we have some limitations put in place to kind of enable everybody to make adequate progress without sort of taking over their entire system. So a user cannot have more than 5 running jobs. There cannot be more than 5 active nodes per user. We do not allow user to have more than 16 GPUs, and we do not allow jobs to run for over 24 hours per job. And there is also a fair share policy that kind of gives priority to those users who haven't run anything recently, and sort of gives a lower priority to those users who have recently run their jobs. This is to make sure that everybody kind of can have access to the system in a more fair way. Now, of course, if you have a paper deadline and you need more time or you need more resources or something like that, we do have a reservation system which enables us to put aside some number of compute nodes with some reservation name that you can use when you need them. So if you have a need for, say, more than 16 GPUs, or to run something for more than 24 hours, or just to be able to get an immediate no access to the system, then we can put a reservation in place. You will need to email us, or you need to join the Slack channel and let us know through the Slack channel about this. One of the use of these reservations is, for example, reserve time on the compute nodes during these training sessions. And in fact, for today's training session, we have a few compute nodes reserved, and the reservation name is HAL_training. So you are welcome to use that reservation name to jump on the nodes and play with them during this training time. Or if we sometimes the machine is used for classes, and then we also make a reservation where students in that class can use. But anyway, so the point here is that if you do not get access to the system and you have urgency of some sort, you can ask us for a reservation. Now, requesting a resource in our system can be a rather complex task. So this is a typical command line to request 4 GPUs, basically the request entire node. You have to specify that you want to use the GPUs. You have to specify how many GPUs and what kind, so V104 of them. You have to specify for how long, 24 hours. You want to say how many nodes. You're asking just one node for this. You want all of the CPU threads. So you also have to say that this is 2 sockets, 2 CPU sockets, all the cores on them, and so on. You also have to say the amount of time, the amount of memory, and all that. So a pretty complex task. So to simplify these things, we wrote a wrapper that kind of enables to get the resources in a much more simpler way. This system was built with the purpose of providing a computational resource for the deep learning community, and typically the workhorse there is a GPU. So if somebody wants to request a resource on that system, that's typically a GPU or a few GPUs. And typically the GPU needs to have some sufficient number of CPU cores to feed it. And typically this also means to have some sufficient amount of memory to be attached to those CPU cores to enable to hold the data set in place. Therefore, we kind of use some pretty straightforward rules to decide what resource you need if you are asking for one GPU. And so we wrote a wrapper, a program called SWRUN, and we advocate everybody using this interface rather than SWRUN directly using SWRUN interface. That is much simpler to use. It requires only 4 options, and some of them actually are even optional. The only option that is truly needed is the partition, and the partition will be GPU1, GPU2, or GPU4, which specifies how many GPUs you want to have. And then you can also have some other additional components, such as for what amount of time, and if you need to run it in a container, and so on. So these are the partition names. So if you use a partition called GPU x1 times 1, meaning GPU x2 times 2 or so, then for each of this, so then you will get one GPU with some amount of CPU cores. So if you request something from partition GPU x1, you will get one GPU with 16 cores attached to it for 4 hours. And if this is not what you need, you can modify the longer script, but by default, what you get is typically sufficient. Also, we have a debug queue that this default allocation goes into. This debug queue is set up there to sort of give you more rapid access if you just want to very quickly test something. The production queues are going to take more time to get into, whereas the debug queue is designed for short-lived jobs that you only typically need for very quick testing. We also provide the ability to put your computations into a container, singularity container in particular. You can specify the container name. We can help you to set up a container if needed. And in this container, you can also ask for what it is that you need to, what partition, how many GPUs you need or something like that. So there are instructions, there are detailed instructions about how to use containers on our wiki page as well. Anyway, so what this means is that instead of writing this very long command line, you can simply write this command line consisting of 1, 2, 3 parameters. And it will give you, will provide exactly the same configuration. It will enable you to get exactly the same resource as this longer line. Moreover, when you run this shorter wrapper-based command line, you also will get a printout of the longer line for this specific set of parameters, which you can then modify according to your needs. So, for example, if you realize that you need, say, fewer tasks, then you can modify this line then later on yourself. Or if you realize that you need something else, you can modify it. But anyway, for most use cases, an interface, SWRUN interface, is sufficient. Okay, so as far as when the time comes to request nodes for the batch computations, we also have a wrapper, SW batch. So instead of using S batch, you can just use SW batch, which also has a much simpler interface. Again, it has some restrictions, but generally speaking, those restrictions are such that they kind of meeting the needs of generic use case for somebody submitting a job to train a neural network model. So, and I will show some examples. So, if you use the direct as batch script, so which you in this case called sample.sb, then these are the parameters you will have to supply. Again, you will have to supply parameters to tell what partition to use, for how much time, how many nodes, and all that. However, if you use our wrapper command, swbatch, you need to write script called sample.swb, and this script will look like this, much shorter. And it will accomplish exactly the same task as this. So, if your generic use case is satisfactory for you, then you don't need to write all this. You can just simply write this shorter script. This example will launch a model called mnist train pytorch.py. With this sort of resources. And so will this script do exactly the same, but the type of resources will be inferred from the partition type, which is GPU X1. Okay, so we do have an interface, a web-based interface to check the resources usage. However, very frequently it's more convenient not to go to that web-based interface, but if you are already in the system, if you logged into the system through SSH, it's frequently more convenient just to run a command which tells you what's going on there. And in fact, SWRUN has this interface. SWRUN has an interface called SQ. So you can type in SQ into the terminal, and SQ will show you the allocation of different nodes and so on. We built a wrapper on top of it called SWQ, which actually takes the output of SQ, which is a text-based output, and generates this sort of visualization plot. This visualization shows for each of the nodes, so we have 16 nodes, how many CPU cores are allocated for different tasks, what users and users, so there is a username and user job ID are using it. So you see, for example, that host 16 is used by several users. There are several users running something there. Other nodes are not used at all. And then it also shows this table for the GPUs. Since each node has 4 GPUs, it shows which GPUs are taken. So, for example, it shows that all of these GPUs in blue are taken, these GPUs are free, and these GPUs are free, and so on. So very quickly, you can kind of get a picture of two things. The status of the cluster, how many GPUs are used, and so on. But also, you can see where your job is. If you submit a job, and it ends up being on hole 5, hole 05, the node 5, then you will see what else is going on the job and which GPUs are used. So it's kind of a visual feedback to indicate that your job is running somewhere. Okay, so here are a few questions that users typically ask about, why and how and so on. So just to clarify those, one of them is why partition GPU X1 doesn't work with SBatch, and why other partitions work only with SWRUN wrapper. The thing is, some of these partition names are designed specifically to work with the wrapper. So GPU X1, X2, and so on, they are partitions designed to work with the wrapper. If you do not want to use our wrapper SWbatch, but instead you want to use SBatch directly, which you're also welcome to do, then there is a different set of partitions. There is a GPU partition and there is CPU partition, and we just allocate resources based on other indicators for those partitions. So when you type in your SWbatch script GPU X1 for partition name, for the SBatch, for batch's purpose, it will be GPU partition. It's just a shortcut that also embeds not only the partition name, but also the execution environment parameters as well. So second question is why I get index error, string index out of range error when using the SWbatch. So the SWRUN wrapper suite requires some packaging like YAML and so on. And in order for these packages to be available in your path or in your environment, you should be submitting your jobs with the default Python environment. So with modulus command, you can kind of modify the environment But there is no point in doing that on the login node, because you are not using login node for computations. You are only using login node maybe to edit the files, maybe compile something if you are developing in C or C++, and then simply connect to the compute nodes, and then run something on the compute nodes, either through interactive mode or through the batch system. But if you are overriding the default environment somehow on the login node, then it's possible that you can remove components which are essential for SW batch. So don't do that. So why my job always under queuing, right? So it's always sitting in the queue and not running. You can actually use, so you can use SWQ to see if your job is running, but then you can also use SQ to get more details about your job. And SQ will tell you what's the reason why your job is in the queue. Maybe you requested with resources which are not yet available. So suppose you ask it for a node with 4 GPUs, but there are no nodes available with 4 GPUs. Then your job will be sitting in the queue and waiting until somebody else's job evacuates or gets done on a given node. So use SQ to check for the exact reason why the job is not available, is not running. Okay, so that's that. So this is a command line based interface, and this interface works well for anybody who is familiar and proficient with a command line interface. We've been able to remotely log into the system and then use just a command line to interact with the system. However, there is a lot of users who are kind of not really into the command line interface, and they would rather prefer to run their applications through something more familiar, or something more simpler, such as Jupyter Notebook or maybe VS Code. And so for that, we do provide interface, which is very popular. A lot of users are using this interface, particularly students who are just simply concerned with developing the model and not wanting to know all the low-level details of how the systems work. And so this interface is built on top of Open on Demand. This is sort of the interface that originally was developed to provide interface to the SWRUN, web-based interface to the SWRUN, but we have a few tools on top of it. So this Open on Demand interface enables to manage data with Files app, so we can copy files from and to the system via web browser. We can edit files. We can also submit and monitor jobs with the Jobs app interface. It is possible to have a command line interface in your web browser as well. So in principle, all you need to work with the system is just the web browser, and this will also give you access to the shell as well. And then, of course, the more useful utilities are Jupyter Notebook and VS Code and some other applications which were deployed, which are very useful for sort of having higher productivity environments to work with the system. So I will slowly go. I will go through some of these examples. So first of all, when you log into the Open on Demand, so if you go to the website, in the second slide of this presentation, I included the slide that gives the link to Open on Demand. So if you go to that link, you will immediately be brought to, actually, when you click on the login button, you will be brought to this web authentication interface. So you need to have an account in the NCSA LDAP system, which you will get when you request an account on the whole system. You log into through that interface. This also requires do second factor authentication. So you will have to set up second factor authentication mechanism of some sort. Typically, it's your cell phone and running a Duo application. So you will be, after you provide correct username and password, you will be redirected to this page. Depending on how you set up your second factor authentication, you probably will get a message on your phone saying to confirm it. Once you confirm this, you will end up logging into this interface, into the HAL on demand.ncsa that will be loaded in the interface. So it looks like this. This web page, just like any other web page, you have access to files application, to the jobs application, to clusters menu, which enables you to use command line interface, and also to interactive applications, which enable you to have access to other applications. So the file interface looks like any other file interface for many other web-based applications. You can explore the file system. You can see what's in your home directory. For these files, you can upload and download them. For each of these files and directories, you have the ability to edit them. So you have a complete control over your files. And there is a built-in text editor, which enables you to edit text files as well. Very simple, but sufficient for very basic tasks. So you can kind of interact with the files on the system through this file application. The jobs application looks like this. So when you submit a job, you can see a status of your job, but you actually can ask status for all jobs for everybody. You can also check status of what's happening in a particular node. So, for example, if you see that your computation is running on node number 8, you can see who else runs something on node number 8. You can see everybody else's jobs. You can see their status. Some of them are completed, some are running. This job is queried, is in the queue. So for whatever reasons, and you can click on this button to get more information about the status of the job as well. So all these tools actually do, they just run SWRUN command line interface underneath, and then report the results back to the web browser. So yeah, basically, you can accomplish exactly the same functionality through SWRUN command line interface, but here it's all hidden behind the web-based interface. You can compose a job of yourself, so you can use this jobs composer application where you can, or interface where you can specify something about your job characteristics, such as what scripts to write, what parameters to use, and so on. So you can create and launch a job from here, from the web-based interface as well. So another interface that you can use, as I mentioned, it is this built-in shell interface, a command line interface. The command line interface is going to place you on a login node. So Open on Demand itself runs on the support server. That is part of the cluster, but it's not a login node. It's an additional server which is there for the purpose of running Open on Demand. When you go into the cluster application, so somewhere here, if you go into the clusters application and see this shell application, you will be opening up a login, interactive login, to the head node. That again will require dual factors. So you'll have to type in your password, and once you type in your password, there will be a dual factor authenticator called. So depending on how you set up it, you will be able to respond to the prompt, and eventually you will log into the login node. And so now you basically have the same interface, command line interface, as if you would have by using SSH, remote login into this cluster. For some users, this is a useful interface to enable to interact with the system both through the interactive tools, web-based tools, and also to maybe monitor something through the command line interface as well. So this is all built in and is available in the web browser. So in principle, you don't need anything other than web browser on your computer to have a complete access to the system. The more interesting applications, of course, are the Jupyter Notebook. So we support both Jupyter Notebook and Jupyter Labs. So the Jupyter Notebook, I think it still runs, but it's kind of becoming somewhat more outdated setup. Jupyter Labs is a little bit more flexible version that gives more flexibility, and you can choose either Notebook or Jupyter Lab, and you can launch it, and then open it in the web browser. So in order to launch a Notebook or Jupyter Lab, you need to specify, first of all, the partition, so CPU or GPU. If you are not going to use GPU, just use the CPU partition. If you are going to use the GPU, choose the GPU partition. You need to tell for how many hours. you need to tell something about how many CPU cores you need and also how many GPUs. So if you need one GPU, you can say that you also need 16 CPU cores because maybe you need to have a data load or something like that. There is also a place to type in the reservation name. And so, for example, so if you are following my tutorial and you are trying to log in into Open On Demand and all that, and you want to launch a Jupyter Notebook, the reservation that we have right now set up for this class, the reservation name is called HAL_training, HAL_training, all lowercase. You are welcome to use that keyword for the reservation, and this will guarantee that you will get access to a computational resource which was put aside specifically for this training. So nobody else can use it unless he knows the reservation name. So once you fill in these fields here and click the launch button, you'll have to wait for a few tenths of seconds, because what's happening, we are basically submitting a job through the job scheduler to one of the compute nodes to launch a Jupyter Notebook for you, and then bring back the interface for it. So you will see something saying that the job is been scheduled. Wait for a moment. Eventually, that message will be updated to say it's scheduled, it's running, and you can click this button to connect to the Jupyter Notebook. So when you click this button, you basically get to your favorite Jupyter Notebook, and you use the Jupyter Notebook to create notebooks and then run them. One important aspect that you have to make a choice right away. Once you connect to Jupyter Notebook, you have to choose the kernel which you will use. Somewhere in this corner, there is a place where you can choose a particular kernel or a particular environment which has a particular set of components set up. So remember, I mentioned that OpenCE environment, which has specific versions of tools like PyTorch and TensorFlow. So you have to choose one of those environments here. They are pre-built and available for you to use. You can consult with a table on our wiki page, which describes that for a given environment, these are the versions of tools which are available. So you kind of have to consult with a table to know exactly what you need and what you're choosing. But that's one of the very first things you need to do. Before you can run a notebook, you have to choose an environment which will bring in all the relevant versions of tools, PyTorch, TensorFlow, or any other modules that are needed for you in your computation. Similarly, Jupyter Lab, you specify the parameters that you want this to be. You click the launch button. Eventually, the Jupyter Lab will be launched, and you can connect to it. So you can, and in fact, when you go and connect, you can have several sessions, each session running on a different compute node, or maybe the same compute node, but basically in an isolated manner that gives you access to a particular system. So this is how the Jupyter Lab will look like. And again, you can open notebooks through Jupyter Lab. You just need to make sure that you choose the kernel that is to be used with your notebook. And then you just have your regular Jupyter Notebook environment, which is pretty intuitive to use. So the caveat here is always to choose the correct environment. Typically, this will be one of the environments which are provided by us, or maybe you can build your own environment. So we use Anaconda package manager on this system. And we have there is a distribution channel for IBM Power9 with NVIDIA GPUs that will bring in all of the properly compiled Anaconda packages, Python packages. There is a caveat that occasionally we run into cases where a specific package may not be supported on Power9 architecture. So don't be surprised if you are using some sort of an obscure package and that package is not supported. It's not in the Anaconda distribution channel for Power9. That happens once in a while for our users. Okay, so we do have a couple of other applications. So one of them is H2O AI. So this application is a collection of tools which enable you to run one of many machine learning models without any coding. So you will end up having a web-based interface which will enable to ask, which will ask you where is your data. So your data is expected to come in some sort of a tabular format, like a spreadsheet table of some sort. Then this interface will ask you, okay, so what is the input in that data and what is the output that you want to predict? It will ask you what is the what kind of model you want to use, and there is a collection of models. It will ask you things like some of these model specific parameters, and it will just simply go and run this model for you. So coding-free environment where you can try different machine learning models without writing any code. Again, launching it is done in the same way as the Jupyter Notebook applications. You can just connect to the web-based interface. So I saw somebody ask a question. So please say what the question is.
I'm not sure if you'll be able to hear me, but I put in the chat.
Oh, there's a question in the chat. Okay.
Yes.
What should we do when a package is not supported? Well, usually, so there are a couple of options here. First of all, the first option is to see if you can use another package. I know it may sound, not the type of answer you want to hear, but what we frequently find that similar functionality is available in other packages. So sometimes you can get away by simply using a different package. Sometimes you can compile the package yourself, and you can add it to the environment yourself. We've seen that happening. And but what happens typically is that you email us, and one of our system administrators look at the package, that packet, and compiles it for you. And makes it available, not only for you, but for other users as well. We've seen that happening as well. And of course, there are cases where there are packages which we just cannot figure out how to compile for this architecture. They have something specific to x86 architecture that does not make them compilable on this architecture. And then in this case, there is little we can do about it. We do have some users who use some very obscure packages that we just could not get to work at all. And in this case, they're just simply not able to use our machine. That's kind of an unfortunate situation. But out of the 1,600 users that we had so far in the system over the past few years, we probably had a handful of cases where we just could not support their packages.
Okay, thank you.
Yeah. So this is what happens when you compile, when you launch H2O tool. You have this sort of workflow environment which says, all right, these are the steps you have to go in order to get your data imported into the system, select the parameters for the data, select the model you want to use, and then select parameters for the model, and then just run. So you kind of go through this steps one by one. So you import the files, you specify what's the input and what's the prediction to be made. You split the frames into multiple subsets for training and for validation and so on. You choose the model. There is a collection of models. These are typically k-nearest neighborhood or some clustering techniques or forest or some sort of simple neural network. And basically, there is a collection of different methods available here. This interface works very well if you really have a tabular data, and the models that you want to use is one of the supported models, and there is a decent number of models which are supported there. So this is an environment that will enable you to process your data with one of these models without writing a single line of code. You use a web-based interface to go through different stages of the pipeline to prepare your data, prepare your model, and then run this model with this tool. So use it if you have a data that is amenable for this sort of and the model that is available. So it's easier to use this type of interface and to write your own code. We do have Tensorboard. Tensorboard is a useful tool to enable you to basically see what's the status of the training job. So you have to use appropriate. You have to instrument your code accordingly to enable to export something to in a way that is accessible by the or acceptable by the Tensorboard interface. But you know there is nothing special here. You instrument your code with what you need to have to enable to write log files for Tensorboard. Then when you launch a Tensorboard through this interface, you have to specify what is the file name that you want to watch that has that log file. So when you launch it and connect it through the interface, you'll get very basic interface from the Tensorboard, which will enable to see what's happening with your training jobs. So there is nothing unusual here. You get a very basic interface for enabling this. Now, this interface may not necessarily be sufficient for what you want to do, so you're welcome to use something like weights and biases, which will give you much more detailed reports. You just have to use weights and biases interface calls or API calls and set up an account somewhere on weights and biases. So, our system does not preclude you from sending data to third-party providers like weights and biases for the purpose of displaying results of training. Now, the other addition which we made, this is very last service, or one of the last services which we added, is the code VS Code support. So previously it was possible for somebody to run VS Code on their own laptop and then just remotely connect to the data server and being able to interact with our cluster through that interface. It is not possible to connect VS Code from your laptop directly to the login node, because login node is also Power9 architecture, and we do not have binaries compiled for the code server for Power9 architecture. Microsoft doesn't provide those. So, however, what we decided to do at one point, we decided to dedicate a server or part of the server to VS Code and basically run the VS Code interface, VS Code server ourselves on that server, and then give you web-based access to VS Code, which actually looks and feels very similar to what you will get if you run it directly on your laptop. So, so this way you don't need to worry about how to connect VS Code to your remote laptop and all that. You simply run it as a service here, code server, and this gives you, access to VS Code interface. You should recognize this as a, this is your VS Code panel. You can install packages, additional extensions to VS Code. You can, have all the other tools, everything. You can also open command line interface, and you basically can use VS Code the same way you would use it if you would launch it yourself from your own laptop and remotely connect or something. But now it doesn't require, this setup does not require having VS Code on your own laptop. All you have to do is just to use a web browser. Now, there are some caveats of how it's used. So if you open command line interface, for example, then you are actually, that interface gives you access to VS Code server, not to the compute node itself. So if you want to run something in the compute node, you still need to submit an interactive job to get access to a compute node. But we do have some documentation about this, so it's easy enough to navigate it. It's just for the first time you need to understand what to do, and then you all set. This code server also is pretty flexible. It enables you to run, for example, even Jupyter notebooks in it. However, these notebooks are not running on the compute nodes. Therefore, there is very, very little value in doing so, because you are just running it on the development node or something. But anyway, so VS Code is fully functional, has all the features and fully customizable and well supported. And once we started to provide the service, very few users needed anything else other than the service of VS Code to develop the code. Okay, so I think this is pretty much all for sort of the slides presentation today. Let me know if you have any questions. Let me know if you have any questions, and I can kind of start to give a more interactive demo of how things work. So this is the reservations that is made for us, HAL_training, that we can use to request resources on our system. Okay, so let me stop sharing for a second. I am going to go to the command line interface. And I will start from the beginning. So, and we will share a command line interface so you can see it for the first time. So when you, so do you see my command line interface here? I can try to make it larger so it's clearer to see. Basically, you know, for the very first time when you get an account on our system, for the very first time you have to log in remotely into one of the login nodes. So you have to provide the username, since my username is in this. So when you do this, this is needed to create the environment, to set up all the computational environment for you to use. So when you log in into this machine, you know, obviously it asks for your password. The password, when you type in, then, you know, that if it's accepted, you will see a message saying that you need to specify what to do with your second factor authentication. So in my case, it's configured to push a message to my phone. The message arrives on the phone. I just click on it to approve this request. And once it's approved, I am on the compute node. I'm on the login node. So this basically shows that I am on the login node. So a few tools which are available for you to use. You know, basically you have a full-blown Linux system that you can use. You can see SQ. You can run SQ to see what jobs are running right now. So there is a whole collection of jobs running by different users in different queues. So if you submitted a job, you can kind of see where you are in this queue. If your job is running, so if it shows one of the node names, it means it's running. If it is not, then it shows the reason for. So for example, this job needs a reservation which is not available or something like that. You could also run SWRUN, and this will give you this graphical interface. So you need to make it a bit larger to see what the status of this cluster. So we have few of these nodes which are available for us, and they are reserved for us to use. So there is nobody running anything right now, but we can start running. So for example, I can go and submit a job to regular queue using SWRUN. So it's actually will go into the debug queue. This is minimally sufficient command line which is needed to submit an interactive job for 4 hours that will go into the debug queue for asking for 1 GPU. So when I run this, you know, I'm sitting in the queue. This is actually showing a couple of things. It's showing this would be the long command line that you would need to type in if you are using SRUN. But with SWRUN, this is all that you have to specify. You know, you're welcome to copy this command line and modify it if you have a need for that. But then, anyway, this is showing that my job is waiting in the queue because there are no freely available resource right now. So we are going to, so I'm going to kill it. So Control-C is going to kill it, and I'm going to add the reservation. So reservation is whole. And if I do this, my job should eventually get executed somewhere. And you actually can see that the new flag compared to this command line, there is a new flag added to this. Yeah, so for whatever reasons, it's not starting, but if there is a valid reservation, if there is a valid reservation, it should typically let you, run in that reservation. Anyways, it looks like it's running. But when this is satisfied, you will see a prompt which is saying that you are now on one of the compute nodes, and you can run there. So once you're on the compute nodes, you can use our module command to see what modules are loaded. If you just simply run list modular list, it will tell you which currently loaded modules are. So, for example, it shows that there is a module which provides the wrapper suite. There is a module which provides all the CUDA tools. There is a module which provides standard development environment and also MPI, open MPI. You can run module avail to see what other modules are generally available. So there are this sort of tools such as Julia, if you need it, HDF5 if you need it, different versions of CUDA if you need it. If you need the debugging tools for CUDA, those are also available as modules. There are different versions of MPI if needed. And then these are the Conda environments which provide different versions of PyTorch, TensorFlow, and other tools. So OpenCE. So I think our latest OpenCE environment is OpenCE 1.7.2. By default, if you just specify OpenCE as the module that you want to load, you will get this version loaded, but then you can specify this as a complete name and it will load this particular module. So that's that. And you can use module load. For example, if you want to load this specific environment, you can do this. What really happens, because this module requires a different version of CUDA, it will also reload the specific CUDA for you as well. So if you now read eval, you will see that this particular module is loaded together with the specific version of CUDA, which is needed for this. And so now this enables you to have access to tools which are needed, which are specific versions of tools in this package, like a specific version of TensorFlow, a specific version of PyTorch, which you can use. Now, somewhere on the HAL wiki, there is a table which specifies what those versions are, so you can kind of look up those versions ahead of time. Okay, but that's it about the command line interface. So, any questions about command line interface? So now I'm going to share the web browser. So this is the wiki page which holds the sort of, there's a master of all of the documents for HAL. What we actually ask, if you use HAL and you end up publishing a paper, we ask you to add this to the acknowledgement, because this is an NSF funded resource. And then the NSF asks us to acknowledge the use of NSF funds for anything useful. And also, if you need to put a reference for HAL, there is actually a paper published about it, so you can reference it this way as well. But anyway, here is sort of the basic documentation which specifies what kind of hardware we have, what kind of versions of software, with links to the specific web pages about all of these things. There is also a collection of our own documentation, but there is actually plenty of other extra pages here which have different aspects of using the system for different purposes. For example, there is a page which describes how to use Ray on HAL, for example, so on. There are also links to other interfaces. So, for example, the monitoring interface. This monitoring interface kind of shows, gives you a web page which shows the use of the system over some period of time, also memory bandwidth and users and jobs. And you can dig down, the GPU usage, you can dig down into each of the nodes utilizations. So there is more info here than this. And what's important for us is that there is a new user guide, which is also somewhere here, which explains exactly step by step what to do when you are only getting started on the system. But let me see what else is here. And yeah, so the most important link is the HAL on demand. Now, we do have a problem right now with Open on Demand due to the certificate expiring. So this Open on Demand requires HTTPS, so secure HTTP access. However, this interface, however, that access requires a certificate, and the certificate expired. So we have a systems administrator who's supposed to replace it anytime soon, typically in your web browser. So this web browser is not happy about it, but let me stop sharing this and pull a different web browser. So Microsoft's web browser has an option to enable to bypass the check for secure shell. And basically, what you end up going to the login page. which is
excuse me, sorry for interrupting. I just like one note. You can also do it from the Google Chrome, but from the incognito tab.
Okay.
I did it from incognito tab and it worked from Google Chrome.
Oh, great. Well, thank you very much for saying that. I was not aware of that workaround, but yeah, that's good. Good. All right. So here you log in with your favorite username and password. Once you log into this interface, there is also a duo push that will be generated. I was logged into this recently, so maybe my duo push is still valid. But anyway, when you get here, you kind of end up on this entry page, which has all the applications listed. So code, Jupyter Lab, which is what we recommend, H2.ai, and also ML Flow. This is another sort of web-based interface to simplify the use of the system. So here you can, as I was mentioning, you have a files management system that enables you to look at all of your files. You have a job management system which enables you to see jobs. So there are two of my jobs which are queued. We can see what's the reason why they are queued and not executed. Something on the resources. So it looks like there is no available resources for this. I'll need to check with the system administrator. We requested some resources for this, but it's not, somehow it's not giving us those resources. But anyway, you can actually see not only your jobs, but all jobs, so for all of the users, and you will see what's happening with all of those. And for somebody's job, you can kind of see what are the parameters of the job. So as I mentioned it, on the clusters tab, you can go to, and so there is a composer which enables you to compose your own jobs. So with this interface, you can provide different characteristics and for your job and submit your own job. So for the this user interface, for the command line interface, you basically have the same interface as if you do through remote shell. But more interesting parts are, of course, this application. So we can try to launch Jupyter Lab. You can specify what environment you want to use. So we kind of embedded this already into the interface as well, compared to the slides. So suppose we want to run this on the debug mode. You want to run it for just 1 hour. With 1 GPU and 4 CPUs. And so I do have reservations of whole, and I will launch this job. So hopefully this will, all this takes a little bit of time because we have to, there are several layers of software here. There is a web server that generates these requests, which go into the SWRUN scheduler, which does something, produces some output, which comes back to the web server, and web server generates something back on top of it. And so, this is what happens when you just submit this job. So it says that it's queued. In fact, we probably can go to the jobs panel to see where my job is. So and so this is when you submit a Jupyter Lab job, you see kind of this is the name of the this job that is executed, and it shows that it's already actually running. So if I come back somewhere here, so the session is starting, so it just takes a little bit of time to get started. Shows what resources you have. Once it's started and then available for you to use, you will see on what login, on what node, all 01, and you can just click this button to connect to it, and it will open you a Jupyter Lab session. Again, it takes a little bit of time to get started, but basically there is a lot that happened underneath. Your SWRUN scheduler got involved to allocate a resource somewhere on hole 1 in this case for you, to set up the tunneling that enables to tunnel the interface from that running on that specific or actually lab server running on that specific compute server, and then tunneling it all the way to the web browser to enable you to see here. And then you can just open environment and open or with your Jupyter notebook or whatever else. Okay, so that's pretty much it. This is all that I wanted to introduce in this tutorial. You are welcome to stay online and explore what you need to explore. Remember that the reservation name is HAL_training, so you can get an easy access to any of these resources. Let me know if you have any questions. But otherwise, this will conclude our tutorial for the day. So thank you very much for coming and listening to it.
So
Thank you.
I had a question about the reservation.
Sure.
How long do we have it for? Is it for the entire duration of the training?
Yeah, the reservation is from 3 p.m. to 5 p.m.
Okay.
Yeah, so the reservation will go away once the time is up. And this is a periodic reservation, meaning that because we are planning to have this sort of trainings of some sort every Wednesday 3 to 5, so this reservation will be active for the rest of the semester every Wednesday 3 to 5.
Thank you.